Hello and welcome to this calculus video. Today we will be talking about the definition of the derivative.
Math 112.
The derivative is one of the fundamental concepts in calculus, and it is used to answer the following question. What is the slope of the tangent line to a curve? Instead of trying to answer this question directly, we ask an easier question. How can we approximate the slope of a tangent line to a curve? For this, we introduce the concept of a secant line. A secant line to a curve is a line that joins two points on that curve. If those 2 points are very close together, then the slope of the secant line is a fair approximation to the slope of a tangent line for nearby points, and we would expect that our approximation would improve if the points become closer. Let's make things a little more concrete by introducing some symbols. Suppose we are interested in the slope of the tangent line to the function f of x at the point x equals a. We are going to approximate the slope of the tangent line to f of x using the secant line through the points a f of a and a plus h f of a plus h. If h is a very small quantity, then the slope of the secant line and the slope of the tangent line will be very close. Geometrically, the secant line and the tangent line will be close to parallel. What is the slope of the secant line? Well, we know 2 points it passes through, so we can use the old rise over run formula and find the slope of the secant line is f of a plus h minus f of a all over h. So that means the slope of the tangent line is approximated by this quantity, and we have more confidence in our approximation as h gets smaller. How can we use this approximation to find the true slope of the tangent line, though? What we would like to do is make the approximation perfect by merging the 2 points we are using for the secant line. We can't do this directly because then we would have 0 over 0 in our slope formula. Instead, we do the next best thing. Rather than setting h equals 0, we let h approach 0 and take the limit. This leads to the definition. The slope of the tangent line is the limit as h approaches 0 of the quantity f of a plus h minus f of a over h, if that limit exists. We denote this quantity f prime of a and call it the derivative of f of x at x equals a. Let's do an example with a specific point and function. Let f of x equal x squared and a equal 2. What is the derivative of f of x at 2? Well, by definition it is the limit as h approaches 0 of 2 plus h squared minus 2 squared all over h. To find the derivative, all we have to do is compute this limit. It might be tempting to plug in h equals 0, but if we do so, the denominator evaluates to 0, so we will be dividing by 0, which is invalid. Instead, we multiply out the squares in the denominator and see that the 4's cancel. Now, everything in the expression has a factor of h, so we cancel this to get the limit as h approaches 0 of 4 plus h, which is 4. So the slope of 2x squared at x equals 2 is 4. So we showed that our limit exists, and we even found its value. When the limit in the definition of the derivative exists at a point, we call the function differentiable at that point. There is an alternate way of expressing the definition of the derivative that for some people is conceptually clearer, but in many specific examples is harder to compute. In the second formulation, instead of the points we take the secant line being labelled a f of a and a plus h f of a plus h, we label them a f of a and z f of z. The slope of the secant line is then f of z minus f of a over z minus a, and the derivative is the limit of this quantity as z approaches a. That's all for today, folks. Today we define the derivative of a function at a point to be the limit of the slopes of secant lines. We saw an example of this in action, and also an alternate formulation of the definition.
Math 112.